Hello, I'm Aishwarya from the Department of AADS. Today I'm going to share some information about unified memory, accelerating matrix addition. So here to perform the matrix additions. So welcome today. We discover how unified memory revolutionizes the way we perform this computation, and this presentation is aimed to equip with a deeper understanding of the unified memory. So its potential is in performance is very high computing, and the challenge of the matrix addition is the basic two thing. One is traditional approaches and the another one is memory bandwidth limitations. And the traditional matrix additions basically involves the separations of CPU and GPU memory spaces, and the data must be transferred between these spaces alone. And for when come to memory bandwidth limitations, it further hinders performance as data transfer will be slow and it will be very inefficient. And the unified memory, it's a game changer. Like we split it into four types: single memory space, direct access, increased bandwidth, and the last one is accelerated performance. Understanding the unified memory basically involves the benefits of unified memory. So, unified memory in actions. First, unified memory significantly enhances the performance when working with the large data. It means it simplifies reduces the development complexity by providing a seamless memory environment. When it comes to unified memory actions, it can be implemented in various contexts such as deep learning models, scientist simulation. So in that case, it will be very helpful for that. And next, matrix addition with unified memory, simplified programming, performance boost. And here is an CUDA. So here we use a CUDA programming model. So first one is CUDA unified memory, and the next one is CUDA kernel, and the next one is performance analysis. So CUDA, NVIDIA's parallel computing platform, provides support for unified memory. It's offering a streamlined and efficient way to manage memory for GPU computation. And in CUDA kernel, it is a function that executes on the GPU alone. Performance of the CUDA code can be using unified memory. It will be more faster and it will be the traditional approaches. And here is an example for a real world example for it. First one is scientific simulations, machine learning, and the image processing. And the next one is the future of unified memory. So first, performance. Unified memory will continue to improve in terms of performance and efficiency. And the second one is integration. Unified memory will become increasingly integrated into the hardware and as well as in the software ecosystem. And in the innovation, it will be tried in more creating the more innovations about this unified memory. And the last slide is about a takeaway. So unified memory revolution is matrix additions. It eliminates memory bottlenecks and accelerated performance, and it will be simply sorting the programming and empowers innovative applications. And so next is about the coding experiment applications. So in basically in the matrix additions, we perform the initialized, so sorry, in with memset means the host reference and the device reference is set as initially 0 explicitly, and in the without memset it is not explicitly initialized. So here is the code. So the overview of this code is to first perform the macros for error checking CUDA, and in the utility functions we want to include the data initially set addition, and we want to verify the result. And in the CUDA kernel, the first function is sum matrix. GPU adds corresponding elements of two matrices in parallel on the GPU. And when comes to main program, it first set the GPU device, allocates unified memory for matrices A and B, and it will be stored it in the result C, and perform matrix addition from the GPU, and we want to measure the time, defines the grid and block configurations of our GPU computation, executes a warm-up kernel for memory migrations, and execute the GPU kernel, measures time. So here is the overall view of this code. And when come to without memset, the same thing. First we want to set the CUDA kernel, some matrix GPU, we want to add two matrices element wise in parallel. In main program, we want to set the device first, initialize GPU, and fetch two properties. Data preparations, we want to prepare the data for matrices and initialize the A and B, and we want to store it in the result C or some other variable, perform matrix addition for the CPU and records execution time, and GPU commands computation. It configures a 2D grid and the block structure. So at last finally we want to verify the result once, then last clean the memory to free up the memory space, and we will the result on the